Okay, you're all set?
Thank you.
Okay, Mr. Cramer, thank you.
All right. This is probably the only talk at this propulsion conference that's not about propulsion, except maybe remotely, in that Jim and Heidi sort of like the transactional interpretation as a way of explaining how the inertia gets transferred between the universe and some object. Anyway, this talk is about quantum mechanics, and it's probably the only quantum mechanics talk you'll ever hear that doesn't have an equation in it. So the structure of the talk is that, first of all, I'm going to talk about what quantum entanglement and non-locality are, which I consider to be the sort of the main sort of counterintuitive parts of quantum mechanics that get in the way of understanding anything else. Then I'm going to talk about the transactional interpretation. Then I'm going to apply it to various quantum optics experiments and so forth to show how it can be used. And finally, I'm going to show some new work on the process of actually forming a transaction in the transactional interpretation. I had originally thought you just sort of had to take the transactions for granted, but I learned from Carver Mead that there's a way of using quantum mechanics to actually show how a transaction emerges as part of the process, and then that will be the end of the talk. Okay, so to get started, here we have an object that's breaking up. Whoops. It's breaking up into a couple of pieces, and in Newtonian mechanics, each of these pieces has a definite momentum, a definite angular momentum, a definite energy, because these are conserved quantities. However, in quantum mechanics, there's a problem, because the uncertainty principle, the quantities that the uncertainty principle talks about are many of the same properties that are conserved in these conservation laws. And so you have this dichotomy between what's uncertain and what has to be conserved. When quantum mechanics systems breaks up, its parts may have indefinite values of energy, momentum, and angular momentum, as described by the uncertainty principle. And after the components are separated, they are not independent, and they may continue to depend on each other even as the parts of the system separate. And so this is the problem. Non-locality comes from these two seemingly conflicting, incompatible aspects. Energy, momentum, angular momentum are conserved quantities in quantum system, and in the absence of external forces and torques, their net values must remain unchanged as the system evolves. However, the wave function describing the emitted particles is subject to the Heisenberg uncertainty principle, and it allows the energy, momentum, and angular momentum to be indefinite and span a whole range of different values. And this non-specificity persists until a measurement collapses the wave function and these values become fixed. And this is a real problem in a multi-body system because measurements in various places all have to agree in order to make the conserved quantities work out. And this is the nature of the EPR paradox. Einstein, Podolsky, and Rosen pointed out that there was this problem in quantum mechanics in about 1935, where these system components have to observe these conservation laws, even though they could be light years apart when the measurements are made. So what do you do about it? Well, first of all, Schrödinger took up the torch immediately and published several papers investigating this property and coined the term entangled. What it means is that the parts, even when the components are separated, the wave functions continue to depend on each other and cannot be separately specified. In particular, they depend on each other in such a way that conserved quantities must add up to the values possessed overall. Einstein derisively called this quantum behavior spooky actions at a distance. He didn't think it was there. And it was a controversy for a long time until people began to do quantum optics experiments to test whether it was there or not, and sure enough, it was. This kind of quantum non-locality is a real property. It's something you have to take into account. And the question is, what's going on? What's the mechanism behind this? And the answer to this question can be provided by the transactional interpretation, which I'll talk about next. Okay, this is a cartoonist friends of mine's version of Wheeler and Feynman as in their 1945 versions when they published the Wheeler-Feynman absorber theory paper. Basically, in conventional electrodynamics, the wave equation is a second-order differential equation in time, and this means it has two solutions. One of the solutions is the one we normally use, which is a wave going forwards in time, carrying an energy and momentum into the future. And the other is a wave going backwards in time, the so-called advance wave, carrying energy and momentum into the past. And the conventional way of dealing with this funny solution is to throw it away and say causality keeps this from happening. Well, causality is not really a boundary condition. It's sort of a prejudice, an observation. And it's not the way mathematicians usually select the solutions of differential equations. And so Wheeler and Feynman decided to look at it. They were trying to solve the self-energy problem. It turns out that didn't work, but anyway, I won't worry about that. But they basically formulated a version of quantum electrodynamics where the advanced solution and the retarded solution are treated even-handedly, and you allow both waves going forwards in time and going backwards in time. And so you get what I like to call a Wheeler-Feynman handshake. Here's an object that has this time is running this way. This object has an excited atom. It sends a retarded wave into the future to a potential absorber over here. It sends, at the same time, because of the Wheeler-Feynman boundary condition, it sends an advanced wave back into the past, going off in this direction. Over here, the absorber receives the wave that's coming at it and makes one that cancels it out here, so these cancel to zero. At the same time, it makes an advance wave which goes back down the track to the point of emission, handshakes with the other, ratifies the transaction, and energy and momentum is transferred and conserved. This is a way of doing electrodynamics which is equivalent to the conventional way. It's not a very good way of doing calculations because you have to know a lot about what's going on in the future, and that sort of prevents you from using it as a calculational tool. Nevertheless, it's completely equivalent to conventional classical electrodynamics. Now, this is where I come into the act. In the early 80s, I realized that you could apply this kind of Wheeler-Feynman logic to quantum mechanics as well. Quantum mechanics has all of these wave functions psi in the formalism, and also the wave function psi star. They're always there together. What is it you do to a wave function when you take its complex conjugate? Well, what you basically do is reverse the direction of time and make it run in the other direction. So one can assume that the psi's that appear in the quantum formalism are retarded waves, and the psi stars that are appearing in the formalism are advanced waves, and they're shaking hands with each other and making transactions that allow things to go forward. Now, I don't have time to go into great detail about the details of the process, but I'll say a few things about it, and you can read further if you want. I'll give you a reference at the end. The transaction is essentially a standing wave that forms in space-time, transferring energy, momentum, and so forth from one particle at one location to another. Here is a three-step process. The emitter sends out an offer wave, which goes into the future. The absorber over here responds to the offer wave by sending a confirmation wave back to the emitter. And this is the first two steps of a multi-step process in which a transaction builds up, going back and forth and back and forth and back and forth until the process goes to completion. What does this do for you? Well, for example, here we have an experiment involving entanglement in which we have a polarized source here a source of polarized light here, which is angular momentum 0. This basically means that when photons go out from the source, they have to be in the same polarization state. If they're right circularly polarized, they both have to be right circularly polarized. If they're left circularly polarized, they both have to be left circularly polarized. If they're linearly polarized, they both have to have the same linear polarization, either vertical or horizontal, and so forth. How is that arranged? You detect one photon over here and measure its polarization. You detect another photon over here and measure its polarization. How does nature do the choreography so that these things always match, no matter what kind of measurement you do on the polarization states? Well, the answer is that there is a transaction that forms going out this way and coming back this way and handshaking both at the source and at the two detector positions. And the only way that transaction can form is if all the bookkeeping works out properly. If this has the right polarization, this has the right polarization, these things match when they come back. So you can form any kind of transaction you want, but only the transactions in which the polarizations match are allowed to form. Okay, so let's apply this to some interpretational paradoxes. Question? The Schrödinger equation is the non-relativistic reduction of what's an underlying relativistic equation, like the Klein-Gordon equation or the Dirac equation, and both of those are second order in time. So basically, if you take the Klein-Gordon equation and reduce it, you get two equations. One of them is the Schrödinger equation, and the other is the complex conjugate of the Schrödinger equation, and the latter has the advanced wave solutions. Okay, so this is probably the first quantum mechanical paradox. In 1927, there was something called the Solvay Conference, in which was sort of the grand opening of quantum mechanics, in which Schrödinger and Dirac and Heisenberg, and others introduced the new quantum mechanics and talked about it. And Einstein raised his hand and he said, I have a problem with this. He said, let's imagine that a source here is emitting a spherically symmetric wave, which is going out into the world and getting progressively bigger and bigger, like a bubble blowing up. And finally it comes to a detector, and the detector detects it. And according to the quantum mechanical solution, or quantum mechanical description that you just gave us, the bubble pops and is not there anymore. Now, how is it that the bubble over here knows that it's supposed to go away when the detection occurs? And he says, this sounds like magic, I don't understand it. And Heisenberg said, oh, Albert, you just don't understand what's going on. What this wave function is not a wave traveling through space. It's a representation of the knowledge of some observer, and the observer doesn't know where the particle went until it gets there. And when the detector detects the particle, then the knowledge changes, and that's why the wave function goes away. This is Heisenberg's knowledge interpretation. It works reasonably well for simple non-locality problems, but it fails miserably when you get into situations where you have a whole lot of different detections going on at the same time. The way the transactional interpretation explains this is that there is a handshake between the source and the detector, transferring the energy and momentum to this detector rather than the others. It could have just as well gone to one of the other detectors, but this is the one it went to, and because of the boundary condition that the source is emitting only one photon, it's only allowed to go to one detector at a time, and it's only allowed to form one of these transactions, and that's why the bubble pops. It doesn't really pop, it keeps on going, but only one transaction is allowed to form. Okay, so this is the famous two-slit experiment. We have a plane wave coming in here. It goes through a slit, spreads it out some. It goes through two slits. The waves from one slit and the other slit form regions where there's constructive and destructive interference, and we get an interference pattern. if we modify this, this situation by putting a polarized, a half wave plate which changes the polarization over one of these slits, then putting a half wave plate over one slit, then the interference pattern is replaced by a diffraction pattern. The interference goes away. The interference is killed by having one polarization coming from one slit and the other polarization coming from the other slit. So that's something one would like to understand and explain. Another aspect of this is that if you watch this interference pattern building up photon by photon, you can put these days, it's fairly easy to do, you can put a detector here which can detect single photons, and you can watch as progressively the interference pattern builds up with more and more and more photons. And what you see is that even though individual photons are coming through and being detected on the screen, together they form the interference pattern. And as you do more and more, the interference pattern becomes clearer and clearer. Richard Feynman described this situation as the central mystery of quantum mechanics, the fact that you can have this wave-like phenomenon building up one photon at a time from individual particles. Okay, so how do you understand that? Well, in the transactional interpretation, if there's no polarizer here, the offer waves can go through both slits, arrive over here and interfere and stimulate the production of a transaction, which goes with the advanced waves going back through both slits, handshaking back to the source, and you get a two-slit process. However, if you put the polarizer there, then the wave coming back here, the retarded wave, advanced wave coming back here has the wrong polarization, cannot participate in the handshake, and so you get a one-slit event, one-slit process rather than a two-slit process, and this kills the interference. So it's easy to understand the thing that was the strange properties of the two-slit experiment using the transactional interpretation. This is another thing proposed by John Wheeler called the delayed choice experiment. We basically have a setup with two slits, and we can either put in a detector plane here which can detect the interference pattern, or we can drop the detector plane, let the light continue on through. Behind the removable detector plane is a lens which brings the images of the two slits to a focus. And so if we do this experiment, we can tell whether the particle went through slit 1 or slit 2 by seeing whether it arrived here or whether it arrived here. If we put the interference plane here, we can see the interference pattern, which tells us that this is the interference as a result of having the particle having the waves go through both slits. So this is a two-path measurement, and this is a one-path measurement. We can either measure wave-like properties or particle-like properties, depending on whether we put this thing up or down. Wheeler's trick is to say, okay, we need to decide whether the light went through both slits or one slit, but we don't decide which experiment to do until the light wave has reached this region here. So we wait till after the waves have had to go through the slit, and then we decide whether we're going to do the first experiment or the second experiment. And so we therefore sort of causally decide whether this was a one-slit event or a two-slit event. How do you explain that with that process? Well, the transactional interpretation doesn't have much problem with that. Let's see, do I have no. Back. If we have a two-slit event, the transaction forms by the retarded waves coming and arriving here, the advanced waves going back, shaking hands along both paths and producing a two-slit event. On the other hand, here, if we detect here, the waves going back are all going back through the lens are all focused on this slit. There's no way that a wave going back this way can reach this point here, so the handshake goes only involves slit 2, and so we get a one path handshake rather than a 2-path handshake. And it doesn't matter when we decide to do the measurement, because having things going in the reverse time direction sort of allows you to stop worrying about when the decision is made. Okay, now I want to talk about a variation of this, and I'm going to ask you a question in a minute. We do this two-slit measure, this which-way measurement I was just describing, with one variation. We have previously measured the interference pattern, and so we put wires in the places where we found the interference minimum. Wherever the thing went to 0, we put a wire there. And we can put these wires in or take them out. Okay, and what we observe is that if we allow only light to go only through one of these slits, the wires block about 6% of the light going through. So in the which way setup, we place a set of wires with 6% opacity in the way. And we place a detector at image 2 over here, and we measure the flux of light that's arriving at this detector. We just integrate all the counts we get here. Okay, now I have a question for the audience. The question is, will interference be present or not in this situation? We're doing a which-way measurement, and option A is that as Niels Bohr taught us, when we do particle-like which-way measurements, all the wave properties are absent, and wave interference and no wave interference can be observed. Therefore, we should see 6% of the flux. Option B is interference is still there. The wires have been placed in minima where there's cancellation and the wave amplitudes are 0. Therefore, the wires will intercept almost no flux. So I'd like to have a show of hands. How many people vote for option A? 2. Okay. How many people vote for option B? Yes, and that's the right answer. When I first encountered this experiment, I went around to my colleagues at the University of Washington posing this question, and almost all of them voted for option A. So you're more sophisticated than the University of Washington physics department. Okay, here's the experimental results. This is what you see with the grid, with no grid and the light going through both slits. You see this sort of baseline image that looks like that. By the way, this work was done by Shahar Afshar while he was a visiting scientist at Harvard, and he had a lot of trouble getting it published because a lot of people didn't like the results of his experiments.
When did you do this?
About 12 years ago. This is what happens when you block this slit and you let light only through this slit. That indeed you see that that 6.6% of the light is removed from the system by these wires when you have only one slit there. Now, when you open the other slit, however, something interesting happens. Namely, you get actually a little more than within errors you get 100%, but what you actually measured is a little more than 100% going through. So opening both slits gives you more or less like this rather than like this, that the loss is less than 0.1% going through the grid. So the wires do not stop the light when you have a two-slit measurement. This is another view of the same experiment. This is when you have one slit open and the wires in. You see all of this junk here caused by scattering from the wires. This is what happens when there's no wires. This is sort of the two slits showing up at the two image points with a little bit of airy scattering, airy interference and so forth around the edges. And this is what happens when you put the wires in with two slits open. Almost nothing happens. You get pretty much the same profile here as here. You don't see all of this stuff caused by the wires. So the conclusion is that interference is still present even when unambiguous which-way measurements are performed. Measuring particle-like behavior does not suppress wave-like behavior if you make careful non-interactive measurements. And it appears that simultaneously one, waves pass through both slits to create the interference, and two, a photon passes through only one slit. So how do we interpret this? Well, the Copenhagen interpretation has some problems because it tells us that quantum interference between waves only occurs when the waves are indistinguishable, that when we have a which-way measurement, the waves are distinguishable and therefore the interference should vanish. And the after-hour experiment falsifies that kind of assertion. The many worlds interpretation has a similar problem because it says that you get interference between worlds only when they're physically, can't occur when they're physically distinguishable. Those two worlds for the wires were physically distinguishable, and so the after-hour experiment falsifies that assertion as well. The transactional interpretation doesn't really have much problem with this. The offer waves are what's interfering. They reach the wires and cancel out, so you can't have flux to the wires because there are no offer waves there to form transactions. Therefore, all the offer waves that can allow to have transactions go all the way through to the detector, and so you should get 100%.
So where did that get published?
Okay, this is another experiment. This was basically the bellwether experiment that convinced the physics world that non-locality was really something that had to be taken seriously. It's the Friedman-Clauser test of Bell's inequalities. Basically, you have an entangled this is not exactly the way they did it because they were dealing with very primitive equipment and their polarizers were giving them trouble. But anyway, this is sort of an idealized way of doing the experiment. You have an entangled two-photon source. It sends a photon to the right and to the left. Here you have a polarizing beam splitter that sends the horizontal polarization state up and the vertical polarization state straight through on both ends. And so then you look at coincidences between these four detectors, the coincidences between this one and this one, this one and this one, this one and this one and this one and that one. And what you find is that when these are perfectly aligned, you would get only HH, in other words, horizontal here and here, or VV here, never HV or VH. Now, this thing is on a rotating base, and you can twist it a little bit and change the angle. And when you do, you're no longer exactly measuring horizontal and vertical polarization in the same system, and so things change a little bit. And as you crank it around by changing the angle theta, you begin to get a small amount of HV or VH coming in that grows as you change the angle. Now, this is where Bell comes in. He showed that if you have certain kinds of local hidden variable theories, and actually the hidden variable doesn't matter very much, it's basically you have any kind of local theory, that there should be a linear dependence on this growth of noise, that the noise should grow linearly with theta, and so it should follow this dotted line here. Quantum mechanics, on the other hand, says this is no different from having a light source with two polarizers in front of it, and you're rotating the polarizers, and so you use Malice's law, which says that the transmission ought to go like the square of the cosine of the angle, and that goes quadratically, and so quantum mechanics predicts a quadratic growth in this noise leakage, whereas Bell's theorem predicts a linear growth. And the experiment has been done many times now and shown to many orders of magnitude that this is right and this is wrong, and this has falsified the idea of local hidden variable theories in various ways. Now, again, what's going on here is that I already talked about this. That what we have is retarded waves going to both detectors and advanced wave handshakes coming back, and the only kinds of handshaking that can happen is when things match properly and conserve angular momentum at the source, because the polarization is dependent on angular momentum conservation. And so there's no problem in understanding the non-locality. It's not that this detector is talking to this detector across a space-like difference. It's that there is the connections along light-like distance intervals going back to the source and ensuring that the conservation laws are being observed. Okay, That's about all I want to say about EPR, but it's not hard to understand using the transactional interpretation. Okay, now this thing is called, one of the things that's usually attributed to the Copenhagen interpretation is that when you make particle-like which-way measurements, it kills interference, okay? And that assertion has been falsified. Now, does that mean the Copenhagen interpretation has been falsified? I guess that's a matter of opinion, but at least that assertion of the Copenhagen interpretation has been shown to be wrong. This is a Mach-Zehnder interferometer. I built these things. They're devilishly hard to align, but when they're properly aligned, if you send a photon here through a beam splitter, the light goes this way and this way, arriving here in such a way that the waves cancel going this direction, but they add going this direction. So all the light, if it's properly aligned, goes from here to here and ends up at D. So this is called the light port, and this is called the dark port, because if everything's properly aligned, you never see light coming out here because of quantum interference. The reason is because to get here, light from here bounces once on this mirror and bounces 3 times on this mirror, and that flips the phase around so that they cancel. Whereas going here, you get 2 bounces going this way and 2 bounces going this way, and so they don't cancel. They reinforce. Okay, now the trick is here, you put a object here. You want to know, is there an object in this lower path? And the people who did this, I'm spacing on their names, but anyway, Vitamin and Elitzer and Vitamin, yeah. Described this as being a way of testing whether there's a photon-sensitive bomb there, which makes it, I guess, more dramatic because it explodes. But anyway, if you put this object here, then 1/2 the time a single photon going through here ends up here, 1/4 of the time it ends up here, and 1/4 of the time it ends up here. So they focus on the events in the dark detector where they end up here, and they point out that when you get a count here, it means that there's an object blocking this path, even though no photon has ever interacted with that object. So this is you're detecting the presence of an object without having it even touched by a photon. 1/4 of the time. And there are also ways of jazzing this up so you can make that ratio a lot higher than 1/4 if you use what's called the quantum Zeno effect. But anyway, the main point is you can detect the presence of an object without ever having a photon interact with it. The transactional interpretation easily explains this, because what you're doing, the reason there was no detections here is because the retarded waves coming this way and the retarded waves, the offer waves coming this way, were canceling and therefore preventing anything from happening. If there's an object here, the offer wave can only get this far. It can't go any further, and so therefore there's no cancellation, and therefore the thing goes through. And so it's not that this thing has been touched by a photon. It's been touched by an offer wave and blocked, and therefore makes this possible. So this is a non-classical a way of getting non-classical knowledge about the presence or absence of a system here, and the transactional interpretation has an easy way of explaining it. Any questions about that? Yeah.
This to me sounds like a way of detecting something. If you were traveling near the speed of light and you want to make sure that you're going to run into something.
You'd have to have something out ahead of you, though. That may be difficult. Okay, this is a variation of the same experiment in which instead of putting a bomb there, we play some games with atoms. You can take an atom in a certain spin state and run it through a Stern-Gerlach magnet, which splits it into its up and down spin components. And so what we've done is to take the atom and and put it in the up direction along the x-axis, and then Stern-Gerlach analyze it along the z-axis so that the up spin intercepts the beam path here, and the down spin doesn't. And then we look over here. Now, what we do is only look when we detect an event in the dark detector over here. And what we find is that even though we have put this atom in the plus state here before we did the experiment. When we look at what the state of the atom is over here after it's been through this process, it is now in half the up state and half the down state, even though no photon ever interacted with it. So this is the same kind of argument involving atomic physics. It's probably impossible to do this experiment because it involves a single trapped atom and it has to stop all photons that come through. But anyway, it's a very interesting Gedanken experiment. And there have been some elaborations of this by Elitzer, putting these kinds of analyzers over here and over here and over here and over here and creating all kinds of complex situations which are hard to describe any way except with the transactional interpretation. Okay, this is what Ray was asking about a minute ago, the quantum eraser experiment. This involves a nonlinear crystal. I've been talking about making entangled photons and some of these things. I haven't told you how you go about making an entangled photon, but one of the standard ways of doing it is with what's called down conversion. You send a pump laser beam through a nonlinear crystal, and part of the time a pair of entangled photons with half the energy and twice the wavelength of the pump come out along specific angles characteristic of the crystal. So here we have a pump laser sending a beam through this crystal, and a pair of entangled photons emerge going this way and that way. We put mirrors down here and send them back in the other direction. The pump laser beam goes on through, is reflected, goes back through, and now it has a second chance to make photons, and it makes with some probability, it makes photons going this way and this way along the same track as the original ones. So if you do this and you move, say this mirror, you can move any of them, you see maxima and minima of interference appearing in both of these detectors as measured in coincidence. You see the count rates go up and down as you move this mirror back and forth. You could also move one of the others back and forth, but you see that these things are interfering because you don't know whether the photon was produced going this way or whether it was produced going that way. Because you don't know, there are equal probabilities of both and they interfere, so you see interference. Now we stick a quarter wave plate in this region here. And what that does is rotate the plane of the polarization by 90 degrees going through and then 90 degrees again. So now this path is labeled as different from this path, and so you can tell the difference between these two photons. There are two different polarization states, and that kills the interference. And so now when you move this thing back and forth, you don't see these maxima and minima going up and down. However, down the line here, and this could be way off here in the distance, we put in a 45-degree polarizing filter there, and that now we have these two different polarization states, one this way and one that way. Now the 45 filter takes this component of this guy and this component of this guy and only lets those through. Now we can have interference again, and the interference comes back. And so you have erased your which way information retroactively after the photons have already arrived at this detector and so forth. So that's the quantum eraser experiment. How do you explain this? Well, it's easy with transactions because it doesn't matter whether you do this early or late. If you have conflicting polarization states, you get transactions forming involving only one path. If you have compatible polarization states, you have transactions forming involving both paths, and so it's very, very easy to explain what's going on in the experiment. Okay, one last problem, which is not usually associated with quantum mechanics, is the so-called black hole information problem. You make you have a Hawking radiation event here where two photons are generated in the strong gravitational gradient at the edge of a black hole, and one of them goes into the black hole and the other doesn't. And these photons are entangled, and so the problem that string theorists and general relativity theorists and others have been worrying about for the last 20 years is what happens how is that entanglement broken by the event horizon of the black hole. And some very prominent spring theorists have made some very wacko assertions about it. These guys, for example, say that whenever you break an entanglement, energy is released. Now, why that's true, I'm not sure, and it makes a firewall, and so anything that tries to go through the firewall is destroyed, and so you don't have to worry about the entanglement anymore. Susskind and Malad. Anyway, these two guys are prominent string theorists, have asserted that wormholes form and the entanglement is preserved by presence of creating wormholes at the event horizon. The problem is that nothing can escape from a black hole, with one exception, and that is that advanced waves have no problems getting out of a black hole because they just retrace the path of the object that went in. And so if you apply the transactional interpretation to this problem, it goes away basically, because the photon that goes through the event horizon and ends up inside can produce an advanced wave that comes right back out through the same path, shakes hands, and the entanglement's preserved, and so the quantum information problem goes away. Okay, I'm going to stop there and talk about how transactions actually form. The Wheeler-Feynman electrodynamics, it's responses from all the absorbers of the future universe arising back together at the emitter that cause the object to radiate. And every future absorber is slightly perturbed by the arrival of an advanced wave, of a retarded wave, and it generates an advanced wave response. And in the quantum domain, this scenario has to be changed to reflect the fact that quantization is there, and the probabilistic nature of quantum behavior. Furthermore, the absorber cannot accept less than a full quantum of energy, but it can be slightly perturbed. In the transactional interpretation, the Wheeler-Feynman process represents sort of the perturbative phase of transaction formation. This is based on Carver-Mead has a very lovely little book called Collective Electrodynamics, and section 5.4 of this book presents this kind of model, which I've built on. Here we have an atom, an emitter atom. It's in a 1- excited state, ready to radiate. Over here we have a possible absorber. It's in the ground state. Notice that these are opposite parity, and first of all, according to the transactional interpretation, the emitter atom in its 1- excited state sends out a retarded offer wave saying, hey, I'm over here and I'm in the 1- excited state, and this goes in various places. And it arrives at this atom and perturbs it slightly, sort of giving a very, very, very tiny amount of amplitude to the 1- state of this atom. And the result of that is that this atom is now in a mixed state. It has a 0+ ground state with a slight perturbation of 1-, and that turns out to make it to produce a time-dependent dipole oscillation in this atom. It sends back the confirmation wave and perturbs the offer wave into the ground state. And so now we have two atoms, both of which are perturbed in different ways. But it turns out that the dipole oscillation that happens is based on a frequency depending on the energy difference between the main state and its perturbation, and that energy difference is the same in both. So we have two dipole oscillators operating at the same frequency under slightly different boundary conditions and sending oscillations back and forth. And so you've got a dipole oscillation that looks something like this. Okay, so this is the 4-vector electromagnetic potential generated by one of these oscillating mixed states that I was talking about. This is, did I miss something? I don't know. Okay, so this is if we have two of these talking to one another, we get a pattern in the electromagnetic potential, electromagnetic 4-vector potential that looks like this. And if you sort of look at the waves in this situation, if you trace the paths of zero phase, you find that you have things going from here to here, all arriving in phase as they go across, traversing all these paths. And the result is that you have an unstable situation. You have two dipole oscillators, and they're each increasing the amplitude progressively of the extra perturbed state on the other side. And so these perturbed levels are getting bigger and bigger and bigger, and it avalanches exponentially. And so what happens is the excited state goes along, and when this happens, it avalanches to the ground state, and the ground state and the other one avalanches this way, and so it changes situations. Now I need to show some movies, and let me see if I can make this system work. Okay, so this is I'm not sure what that means. This is an one of the oscillating dipoles. This is a three-dimensional view of the same oscillating dipole. On my computer, these run continuously instead of killing like that. But anyway, this is the radiating one dipole radiating and. Okay, maybe that's yeah. Okay. Is that? Yeah, there we go. So you can see the waves emanating from the emitter and going progressively out and converging on the absorber here as the energy and momentum are transferred through the four-vector potential in this case. And how do I kill this? And this is the same thing in 3 dimensions. And finally, we can project out the excited state wave function of the system. And here is the excited state wave function, and it transfers over here. And here's the same thing as seen in the 3 dimensions. Okay, so this is a Mathematica notebook that implements the mathematics using conventional quantum mechanics, except that we're using waves going in both time directions to show it. And so the conclusions are that the transactional interpretation provides a rational way of visualizing and understanding mechanisms behind entanglement, non-locality, and wave function collapse. The plethora of interpretational paradoxes and other non-classical quantum optics experiment results can all be understood by applying the transactional interpretation. The process of transaction formation, at least in simple cases, emerges directly from the application of standard quantum mechanics to advanced retarded wave handshakes processes as it builds and avalanches to completion. And finally, as the mattress commercial says, why buy your quantum interpretation anywhere else? The other thing I should say is that this is the only interpretation that comes with its own operating manual, which is my reference. This is my book, The Quantum Handshake, which looks like this and is available from Amazon and also directly from Springer, particularly if you want to pay in euros. It's a bit cheaper in euros than it is in dollars for some reason. Okay, and I will stop there and answer questions.
So, John, we were talking on Tuesday night about pilot wave theory.
Yes, Bowman and mechanics. Yes, I have a.
It's starting to as a resurgence of interest. I was wondering how it correlates.
Okay, let me say a little bit about Bowman and mechanics. The Bohmian mechanics basically takes the equations of quantum mechanics and manipulates them in peculiar ways and generates what Bohm calls a quantum potential, which modifies the trajectories of particles. This is a figure taken from Bohm and Hiley, a book about the Bohmian interpretation that was published the year after Bohm died, showing a two-slit system. Actually, there's supposed to be electrons coming through the two slits, but they're non-interacting electrons. There's no electric charge associated with them. And these lines here represent what are called Bohmian trajectories. Basically, what you do is you take the quantum mechanical wave function and apply the vector momentum operator to it to get what the local momentum is at a particular point in space. You make a vector point in that direction and take a step. Then you do it again and take another step and so forth. It's sort of like plotting field lines. And like field lines, the trajectories never cross. So whatever comes through this slit stays on this side. Whatever comes through this slit stays on this side. If you really believe that an electron coming through this slit never goes over here, then I have a nice bridge to Brooklyn and New York that I think that you would find an excellent investment possibility. I figured out how to calculate these things for a cross laser beam, and what I found was that if you take a pair of laser beams and cross them so that they interfere, the Bohmian trajectories turn the corner like this and they never cross over there either. So I propose an experiment for testing and falsifying the Bohm interpretation in which you do this. You have a laser beam, you break it into two pieces and make them cross at two places, and according to the Bohmian trajectories, the photons ought to turn the corner here and go this way, and turn the corner here and go this way, and arrive at the detector earlier than they would if they, according to quantum mechanics, these things ignore one another, bounce here and go here, and take the longer path. So it should be possible to test and falsify the Bohm interpretation by doing a time of flight measurement. Now, this particular setup is a sort of schematic. It has a few problems. You really want these angles here to be smaller, and the chopping creates a little bit of problem by introducing extra frequency components, but those are all things that can be dealt with, and I think this is a feasible experiment, and one of these days maybe I'll even look into actually performing it. But what my point is that I think the Bohm interpretation is telling us some wrong things. I believe by no stretch of the imagination, do real photons in a cross laser beam do things like that and turn corners? And I think that's sort of physically unreasonable, and I'm not sure how the Bohmians managed to swallow that and really believe it.
You know about the experiment of my former student Ephraim Steinberg, who at Toronto showed that the Bohmian trajectories with this dark middle thing really...
Well, the thing about these experiments that claim to show Bohmian trajectories are that they're using weak measurements which are subject to the uncertainty principle, and the Bohmian trajectories violate the uncertainty principle with extreme prejudice. So I think the claim that you're seeing Bohmian trajectories can't be right because weak measurements would not allow you to see a Bohmian trajectory because they're subject to the uncertainty principle.
I'd love to hear Ephraim's response to that. I don't know what he would say.
Anyway, enough about the Bohmian interpretation. Anybody have any questions about anything else I was saying? Yeah.
I was just going to comment. I really like the suggestion for an alternate experiment that you could actually verify with, but I sort of find the appeal to incredulity is not a very good argument in quantum mechanics. The whole field is based on things that I wouldn't swallow.
That's a fair comment. Yes, the whole thing is subject to believing funny things, and so.
I have a question, John, about Heidi's extension of your work to what she calls the the gravitational absorber theory, in which you get backwards propagation of gravitational waves, essentially, from the far future.
Yeah, well, obviously the problem is that we don't really have a theory of quantum gravity that we can hang on to and do real calculations with it. So at some level you have to do the best you can, and I don't know what to say beyond that, because there is no theory of quantum gravity that we can look at to see how things work. But one would think that to the extent that there are wave phenomena associated with gravity, they ought to work the same way.
Yeah, but well, maybe I should address this question later when.
Yeah, maybe you should ask Heidi.
Heidi, but I'd like to hear your response. In the absorber theory, the Wheeler-Feynman absorber theory, it's very reasonable to believe that the universe is dark outside. I mean, it's a boundary condition that we observe empirically. When you look out at the sky at night, it's dark, and so it's a reasonable asymptotic boundary condition. Okay. I mean, no, you have to make an assumption of the absorber theory concerning the far future. Otherwise, you don't get a consistent theory, it seems to me.
I don't exactly understand what you said, but there's the problem that Wheeler and Feynman assume that the absorbers lie in the future, not in the past. Is that what you're saying? Yeah. And yet, the past is hot and dense, and the future is black and open. Yes. And so there's an arrow. There's an arrow that they sort of ad hoc chose.
Yeah, exactly.
Okay. Okay. I can refer you to some papers that I wrote on the subject a while back. But one of the things to say is, what is it that asymmetrizes the universe? Well, if you imagine that you make advanced waves and they go back in the direction of the past, how far can they go? Well, they can't go past the Big Bang. So the Big Bang represents a sort of a stopping point that they can't go any further. And in waveguide transmission line theory, if you have a short in a transmission line, what you get is a reflection that goes back the other way. So my view is that the arrow of time is created by the fact that we have a Big Bang singularity in our past and an open universe in our future. So you can't have the advanced waves going that way. And so things have to move forward, and that's what determines the direction of time. And I have a paper that makes those arguments that I published in PhysRev many years ago.
Oh, interesting. Okay, thank you.
Okay, if there's no further questions, can we thank the speaker?